For the next example, we're going to recall the definition for the absolute value of x. Notice this definition is case sensitive. If x is greater than or equal to 0, then the absolute value of x is indeed equal to x. If x is less than 0, then the absolute value of x is actually the opposite of x. And we're going to combine this definition with this new definition, the square root of x to the even powers. Now, the square root of x to the even powers is going to be case sensitive only for certain n values, okay? The n values here stands for a value that is in the set of natural numbers. If you forgot the set of natural numbers, I could write it for you. The set of natural numbers is equal to the set containing 1, 2, 3, and so on. Now, using the definitions above, we're going to go ahead and write out the square root of x squared. Notice this is for n equals 1. And for the square root of x squared, we're going to know its absolute value of x. This is going to be piecewise. Okay, it's x if x is greater than or equal to 0, and it's opposite of x if your x values are negative. What about n equals 3? What would be the square root of x to the 6? That will be the absolute value of x to the third. Once again, notice it is case sensitive. And we're going to use this fact, or we're going to use this definition in the upcoming example. If you're wondering how you would continue this pattern, you would actually write n equals 5, and you will evaluate the square root of x to the 10th, and so on and so forth. The next n value would be 7, the next n value would be 9, the next n value would be 11, and you would continue writing out these piecewise definitions. Let's go ahead and look at the next example. Now, instead of graphing these functions in the form of fractions, we're going to try to look at the n behavior by doing algebra. And algebra is a form of magic. We're going to perform sophisticated algebra here and see if we could evaluate this limit, or at least see the left n behavior. Now, if you check its form, you're going to try to estimate the form here by looking at the leading degree or the highest degree of the numerator. Now, the denominator is not even a polynomial, but you could try to estimate it by realizing, okay, you know, what happens if you take a very negative large number and raise it to the third power? You're going to get a form of, let's say, negative infinity. You're going to get a form of negative infinity. And then if you had to estimate the bottom, you probably would estimate it as positive infinity. This is still indeterminate. So instead, what we're going to do is use some magic. Remember here, magic just means algebra. And we're going to notice the domain of x values that are approaching negative infinity. And we're going to keep the numerator to be the same. But try to simplify the denominator. Okay, try. Okay, we're going to try to factor out a 25x to the 6 and see what's left. And so there's the factored form underneath that radical. And now you got to pay very, very close attention to this domain. As x values are approaching negative infinity, what would happen to the square root of x to the 6th? What would happen to the square root of x to the 6th if your x values are approaching negative infinity? In fact, it would be that. Okay, so that is our substitution. We're going to realize it's this, and we're going to substitute with that. So here we go. Let's do our magic. And then we write whatever's left in that radical. Now remember these properties from algebra. That's what we're using here. And after this algebra manipulation, we're ready to check its form again. So the top still looks like negative infinity, and the bottom, you have to realize this is relatively small compared to this. So we're going to just concentrate on this. That looks like positive infinity. So that is indeterminate still. Now that's still indeterminate. What we're going to do is do a little bit more algebra to make this magically appealing. We're going to do that. I'm going to multiply by another name of 1 and see what happens. And go ahead and check the form now. If you check the form now, you're trying to work on your limit laws. You're trying to be 2 steps ahead. And so what's 2 steps ahead here? You have to check the form of the numerator and then check the form of the denominator. So the numerator now has a form of positive 10. And the denominator now has a form of negative 5. That's a determinate form. More specifically, if that was too fast, I could tell you that I estimated negative 10 subtract very small plus very small over what? The square root of 1 plus very small plus very small. Now notice I'm using the symbol 0 to represent very small, so I'll put that in a bubble. Now since that limit exists in the numerator and exists in the denominator, you could write an extra step here. I shouldn't say an extra step, it's a beautiful step. And there you go. This limit is going to be 10 over negative 5, which will yield negative 2. We can make a very important conclusion. Therefore, a horizontal asymptote is y equals negative 2. Now, why don't we look at the right end behavior? In other words, let's see what happens to the x values as x approaches positive infinity. So same function, so very, very similar idea, but you do have to pay close attention to what x values are you analyzing. So let's recap that algebra again. This time, this is x is approaching infinity. So we have 10x cubed minus 3x squared plus 8. Put this over what? This is 5. And in this case, we have x to the third power. And then we have that radical left. We'll do some magic. Do some algebra here, that will work. And algebra is such a beautiful language, especially when you understand it. It allows you to learn so much more, like a subject called calculus. Once again, if you're thinking 2 steps ahead, you're trying to see if the form actually is appropriate. In other words, is it determinate or indeterminate? And notice here 0 represents the concept of very small. That's why I put this in a bubble. It's not really 0. We're just approaching 0. Now, what we're really ultimately approaching is 10 over 5. And what's 10 over 5? That is in fact 2. Therefore, a horizontal asymptote here for the function is y equals 2. So, were there any horizontal asymptotes? Yes. In fact, there were 2 of them. Namely, y equals negative 2 is the name of one horizontal asymptote, and the other name was y equals positive 2. This last example here is just a recap of a technique you may have learned earlier, and that is called the squeeze theorem. But notice this time the squeeze theorem involves an x approaching infinity. So in order to exercise or execute the squeeze theorem, you have to write a number of sentences in a very specific order and make sure that you have the squeeze theorem memorized so that you know why you're writing those sentences. The first thing you're going to do is note that the amplitude for sine of x is at most 1. In fact, it is 1. So, but look at all the y values. All the y values are at most 1. And that yields another inequality. It yields this inequality. I'm going to put a period there. Now, what do you know about your x values? Your x values are actually approaching infinity. Not only are they approaching infinity, you know something about the square root of x. From algebra, you know that the square root of x has a domain of x is greater than or equal to 0. But since it's in the denominator, it has strictly greater than 0. So our next sentence will go something like this. Since 1 over the square root of x is strictly positive, we now have this inequality. And you even know the limits of the functions on the far left. I should say, you know the limit for the function on the far left, and you know the limit for the function on the far right of that inequality. You know that is a finite number, and that finite number is called 0. Finally, the last sentence. By the squeeze theorem, what can you conclude about the function in between? That function in between is squeezed between the limits there. That means the limit, as x approaches very large, of 1 over square root of x times sine x has to go to 0. And that is a proof for finding the evaluation of this limit. Make sure you're writing those sentences in order. Make sure you have a capital letter and a period to indicate those sentences.